In Module 4, Section 3, we're going to go over the basic techniques of multiplying radical expressions. And there are some simple rules that we follow, and we'll get started. Now, the key to all of these is that your index number generally has to be the same. When it's different, we use a little different technique. We use the fractional exponent technique. But here, index numbers are the same. We then just multiply our radicants and get 14. Now remember, we can look at the square root of 14 as the square root of 2 times the square root of 7. So this can go either way. Now notice these are conjugates. So this is just going to be when they're multiplied. And we don't really need a parenthesis there. I got carried away. This will just be x squared minus 4. Now if you took it out of the parentheses, or out of the radical sign, you would have to put parentheses. Now there again, our index number is 3, so we just put it under a common radical sign by multiplying our radicants, which is 45. And here, under a common radical sign, with index number 4, we have 18a over 5b. Alright, so some very easy principles here, and let's move on. Now here we need a protocol to do these, keeping in mind what we just had. We want to simplify by factoring. So the basic rule is to write two sets of radical signs, and you want to see if in this first radical area you have a factor of 98 that is a perfect square. So if you divide this by 2, you get 49, which is a perfect square, and the part that isn't goes in the other radical sign. So then you take the square root of 49, which is 7, the square root of 2. So you have simplified this radical expression by factoring it into two parts, where under one radical sign you have any perfect square factor, and usually the largest perfect square factor. Okay, so our pattern, we're going to set up two radical signs, and they're the same index number. Now we look at the number 8. Is there a perfect square factor of 8? And yes, you'll say it's 4. And what's left over is 2. Now how about the x? That's not a perfect square, so we're going to put the x over here. Now how about y to the third? Is there a perfect square factor? Well, any power of 2 here, so y to the second would be a perfect square factor, and what would be left over here is y. So now we take the square root of that, and we get 2y times the square root of this, 2xy. And we have simplified this by factoring. Now again, don't get concerned if there's a negative under the radical sign. It's perfectly legal if your index number is 5. So you want to divide this into two radical parts, both with the same index number. Now if I divide this, I had to pause a little bit to think. This is divisible by 3. And if I take a 3 out of there, I get 32. My pen doesn't always cooperate here. 32 times 3. Because 32 is a perfect fifth power. Now, 2 to the fifth is 32. So the fifth root of a negative 32 is a negative 2, the fifth root of 3. Now these others were a little easy. This one was a little more challenging. You had to see if there was a perfect fifth. And through practice you'll get used to some that are. Let's go on. Now in this case it's a little bit tricky, but let's take it in steps. So we're going to first factor out the greatest common factor in my radicand, which happens to be 2x. Then this becomes x squared plus 6x plus 9. Now, do you see here that this is a perfect square trinomial that we now will factor into two parts? This factors into x plus 3, the quantity squared, and this is what doesn't factor at all anymore. And now we have, again, this is a little challenging. We had to see that we could take a 2x out of there. This is a perfect square trinomial that we get this. Now, when we get this, and again, we're going to use our principles here, any real number, that this is x plus 3 in absolute value, and then this is 2x. Now, if you didn't put the absolute value signs here, which are a grouping symbol, you'd have to at least use parentheses, because it would be this times this. If you didn't use some sort of grouping symbol, you would have the x and then only the 3 times this. So this is the proper way to write it. But in an answer, I would give you some partial credit for doing all that you've done so far. All right, let's go on. Now a few more examples where we're going to use a set of radical signs. Now, what's a perfect square here? Well, any even power. So a to the 10th, b to the 8th, and there will be a b left over here, c to the 14th, and there would be a c left over there. Now, in each of these, we're just going to divide by 2. So this would be a to the 5th, b to the 4th, c to the 7th, dividing each of these by 2, and this is BC. All right, let's go on to letter F. Again, two sets of radical signs. And we're showing you the method for factoring and then simplifying. We're going to divide this by 2 and get 27, which is a perfect cube. And then now anything that's divisible by 3 is a perfect cube. So x to the 6th here, and we have x to the 2nd left over. Y to the 9th, z to the 9th, with a z left over. So again, we're factoring that by separating it into two factors. One that is a perfect cube, and whatever's left over. So the cube root of 27 is 3. Now we just divide our exponents by 3. X squared, y to the 3rd, z to the 3rd, and then the 3rd root of 2x squared z. And I can imagine it's difficult putting all of this into MATLAB, but again, just take your time, check your work. You want to get the full credit. Now, a little bit of bringing what we've just had into here. Another way of looking at it is we want to multiply and simplify. So if we factor this, this is 2 times 3, and if we factor this, this is going to be 2 times 5. Now notice we have 2 and a 2, which now is a perfect square, 4, and what's left is 15. So now we take the square root of 4, which is 2, the square root of 15. Now if you multiplied this, this would be 60, and then you would say, what's a perfect square factor of 60? And that would be 4 times 15. This is just another way of looking at it. Alright, let's do this one. This is 5 now. The 3rd root of, I'm going to factor the 36 into 6 times 6, and then this is times 2, the cube root of 6. Now again, we're asked to simplify this. Well, we know our 5 times 2 is 10, and then we have the 3rd root, and I'm going to write these 6 3's using exponential notation. And notice when our index number and the exponent to which we're raising the radicand are the same, it just becomes the radicand. So this is 10 times 6, and that is 60. So these are the steps that I've used and the sequence that results in our answer. Alright, let's look over here. So we have in our first one 3 times 3, and I have to put a 4 there, and this is x y to the 10th. Now some of this you can do mentally, and this is 3 times 3, x to the 2nd, y to the 3rd. So now I'm going to put all of my fourths under one radical sign, and whatever's left under the other radical sign. So I have 3 times 3 times 3 times 3. I could put an 81 here, or I could just put 3 to the 4th. That's a perfect fourth. Now I have x and x to the 2nd. That's never going to reach x to the 4th. So that x to the 3rd goes right there. Now I have y to the 10th and y to the 13th. Well, y to the third is y to the 13th, and a perfect fourth is y to the 12th. That is a multiple of 4, and there's one y left over. So x to the third, which is right there, which is not a perfect fourth, y to the 13th, but then I'm putting my perfect fourths under one radical sign and whatever's left under the other. So this becomes 3 when I take the fourth root. Divide the 12 by 4, I get y to the third, and then the fourth root of x to the third y. And there is the strategy, the protocol, to get our answer.